Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java native interface documentation that Oracle provides. And I'm going to continue with chapter 2. So implementing local references. To implement local references, the Java VM creates a registry for each transition of control from Java to a native method. A registry maps non-movable local references to Java objects and keeps the objects from being garbage collector. So when we create local references in a C++ code, when we are doing JNI development, so obviously we don't want the garbage collection to interfere. So JVM has to keep track of those and tell garbage collector to hands off for now. All Java objects passed to the native method, including those that are returned as the results of JNI function calls, are automatically added to the registry. The registry is deleted after the native method returns, allowing all of these entries to be garbage collected. There are different ways to implement a registry, such as using a table, a linked list, or a hash table. Although reference counting may be used to avoid duplicated entries in the registry, a JNI implementation is not obliged to detect and collapse duplicate entries. Note that local references cannot be faithfully implemented by conservatively scanning the native stack. The native code may store local references into global or heap data structures. All right. So that was the discussion of local and global references. And again, it's not a very important topic because usually VM can handle them in the JNI codes that we develop. So we don't need to worry about those to some extent. Accessing Java objects. So we have discussed these in a lot of details. Accessing fields, manipulating fields, modifying fields, accessing methods, calling methods. The JNI provides a rich set of accessor functions on global and local references. This means that the same native method implementation works no matter how the VM represents Java objects internally. This is a crucial reason why the JNI can be supported by a wide variety of VM implementations. The overhead of using accessor functions through opaque references is higher than that of direct access to C data structures. So we're using basically we're using opaque references and accessor functions. And again, if you recall, the way it works is that we use a mechanism in JNI which is very similar to Java reflection. So it has more indirection. And when you have more indirections, then it adds generality in the cost of like call overhead, right? So it has some overhead. We believe that in most cases, Java programmers use native methods to perform non-trivial tasks, right? So if I have a math library that does a lot of computations, the overhead of calling or accessing Java features are probably negligible compared to the actual task that being done in C++. That overshadow the overhead of this interface, right? So when you're developing JNI, always ask yourself, is the C++ code, is the reason that I'm going to native code is for computation intensive or non-trivial tasks? Otherwise, the JIT compiler of Java is very well able to handle trivial tasks, right? A for loop, something like that. But if that's something that we really have a very highly optimized C or C++ library, then we should definitely think about the JNI route. Accessing primitive arrays. So let's say arrays, working with primitive arrays. So this is what we talked about. Primitive arrays are easy to work with because the primitive types of C++ and Java have a very direct relation to each other. They map to each other. That's why it's very nice to work with them. The difference here is that a primitive array in Java is an object. A primitive array in C and C++ is just like a pointer, right? So they don't map to each other, and we don't care actually because we're using the indirection that JNI provides. So we work with the JNI interface pointer or JNI environment pointer, which I always call it JVM, and the functions that it provides for us to get access to them inside the JVM. Accessing primitive arrays. This overhead is not acceptable for large Java objects containing many primitive data types, such as integer arrays and strings. Consider native methods that are used to perform vector and matrix calculations. it would be grossly inefficient to iterate through a Java array and retrieve every element with a function call. And we saw that the problem was that by default, if we ask JVM to give us access to a primitive array on Java heap, we most likely don't get a direct access to it. So JVM behind the scenes creates probably a copy and gives us an access to the copy, right? And that's a little bit inefficient if the array is very large. So the solution was that JNI provides critical access to primitive arrays also, which is the best solution for us because we get direct access to it, but we have to be careful what we're doing with those direct accesses. One solution introduces a notion of pinning so that the native method can ask VM to pin down the contents of an array. The native method then receives a direct pointer to the elements. So let me back up a little bit and talk about the actual working with primitive arrays. As we discussed in the lectures, we said that primitives of the C++ map directly to the primitives of Java, which is good. So Boolean maps to JBoolean, byte, JByte, char, JChar, double, JDouble, float, JFloat, int, JInt, long, JLong, short, JLong, and void is void. And this is great because we don't have any problem really with dealing with JNI primitives because they're just a type def of actual C++ primitive. For example, JBoolean, the Boolean in Java is supposed to be 1 byte unsigned integer. That's why JBoolean is defined as an unsigned char in C++. It's just a type def. Byte is supposed to be 8 bits or 1 byte signed. So JByte is obviously a type def of signed char in C++. JChar in Java character is supposed to be 2 bytes because it's UTF-16. So it doesn't map directly to char. Instead, JChar is a type def of unsigned short because it's an unsigned integer, but it's 2 bytes or 16 bits. Double, JDouble map to each other, float, JFloat map to each other, int and JInt map to each other. And again, integers mostly like JInt and then JLong, you mostly find these in the machine dependent header file of the JNI, but like double, float is or JBoolean, you find them in the JNI.h. So they're pretty much independent of the platform. Almost all, I guess all the recent platforms or all the platforms in the past 5-10 years, they all support like double as a 64-bit, float as a 32-bit, so we don't need to worry really about them. But obviously integer and long are different stories. So Java has to guarantee that the JInt is 32-bit signed and JLong is 64-bit signed. All right. So double becomes JDouble, float, JFloat, int, JInt, signed integer, primitives array. A double array in Java is an object. So it maps to a JDouble array handle or JDouble array reference. A float array in Java maps to JFloat array, JInt array, J whatever type, primitive type array. That's the mapping from Java objects, Java primitive arrays to C++. All these types are subtypes of JObject, and again, JObject is a generic handle in C++ in JNI. And then we ask our JVM to create a double array for us. For example, JVM new double array, we pass in a JInt as length. And again, once we do that, we can ask JVM to, if we have a C or C++ raw array, we can copy its element into this double array. So JVM set double array region. Any function that basically ends with region, it means it takes something and copies it into something else. So we give the reference to our J array, and then from the index 0 to index len, from index 0, this is the start index, and the next one is the length of the array, and these two are JInt. Note that the JNI functions types are not size t, which is a standard type that we use in C++. They're all JInt, so you have to be careful about them. And then the C array, and this copies the C array into the J array, right? And then if you want to just read a double array, we use the get double array region, and a JVM copies the Java array into a C array. So a copy, we are very well aware that a copy will happen, but at least we directly get all the elements. But then if the Java array is very large, this is a very inefficient way of getting access to the elements because we're copying to a C array. Alright, so the native method then receives a direct pointer to the element. This approach, however, has two implications. The garbage collector must support pinning. The VM must lay out primitive arrays contiguously in memory, although this is the most natural, and I guess it's definitely the default in like the OpenJDK implementation, the reference implementation. Although this is the most natural implementation for most primitive arrays, Boolean arrays can be implemented as packed or unpacked. Therefore, native code that relies on the exact layout of Boolean arrays will not be portable. We adopt a compromise that overcomes both of the above problems. First, we provide a set of functions to copy primitive array elements between a segment of a Java array and a native memory buffer. And again, that's the set double array region and get double array region. These this double is obviously changes for other primitives: set int array region, set boolean array region, set float array region, and then get, set and get array region with whatever primitive type that we're using. And these just copy elements between a Java array reference and a C array reference, or pointer basically. Use these functions if a native method needs access to only a small number of elements in a large array. So if you only want to access a small number of elements in a large array, this copy doesn't really have any overhead, because remember, these functions, set type array region and get type array region, there is an explicit copying happens, and we are very well aware of it. We tell JVM copy the J array into C array, or copy the C array into J array. Second, programmers can use another set of functions to retrieve a pinned down version of array element. So when you pin down, the garbage collector cannot move it while we are in the native code. Keep in mind that these functions may require the Java VM to perform a storage allocation and copying. So when we pin it down, JVM gives us a direct pointer to that primitive array on the Java heap. That's a direct access. So no copying happens. In order for us to get access to the elements, we don't need to copy them into a native array, right? And that's the primitive type, so that's the critical access. Critical access. So we talked about the regular access versus critical access, and we said that if we use the get array region and set array region, there is an explicit copying happens. Although when we do a get double array region, there is a isCopy flag, and we check that it always comes back true, which means the JVM actually creates a copy, right? So get double array region, this is definite copy. Get double array elements. Get double array elements, basically it gives us a raw pointer. J double pointer is a primitive pointer, but it has a JCopy flag, isCopy flag, and when we tested it, we saw that our JVM, like the Oracle JVM, actually creates a copy. So when we use these get double array regions for any primitive type, it doesn't give us a direct pointer. Although it gives us a raw pointer, it's not a direct pointer to the Java heap. JVM creates a copy of the array using the clone. Remember that the clone function is by default implemented intrinsically inside the JVM for all the primitive array types. And that's very interesting that that's the only place where the clone has been implemented, right? So JVM knows how to copy primitive arrays, so uses that clone, creates a clone of the original array and gives us a pointer to the cloned, and it's a copy. And we said that whenever a JNI function gives us a raw pointer, we have to use the release function to clean that up. It's a manual memory management. So get double array region, then we have to call the release double array elements. But this is still not a direct pointer. So what this says here is that JNI can also give us the primitive access critical, get primitive array critical, J array, and then it returns a void pointer. Based on the type of primitive, it gives us a direct raw pointer. We should typecast it, and this is a direct copy. So when we tested this, isCopy comes back false, which means this is not a pointer to a copy of the array. This is a pointer to the array, and the JVM has pinned down that array in the memory, and it has told the garbage collector not to touch that array, not to move it around in the Java heap. All right. So second, programmers can use another set of functions to retrieve a pinned down version of an array elements. Keep in mind that these functions may require the Java VM to perform storage, allocation, and copying. Whether these functions in fact copy the array depends on the VM implementation. That's why they have this isCopy flag, both for the get double array elements and get primitive array critical. So you have to test it based on the VM that you're using. If it's Oracle VM, then almost 100% we know that this get double array elements that gives us a raw pointer in fact creates a copy, creates a clone. Get primitive array critical doesn't create a copy, so it's a direct access. But that's why we have this isCopy, because they already knew that the VM can change from one vendor to another. Whether these functions in fact copy the array depends on the VM implementation as follows. If the garbage collector supports pinning and the layout of the array is the same as expected by the native method, then no copying is needed. Otherwise, the array is copied to a non-movable memory block, for example in the C heap, and the necessary format conversion is performed, a pointer to the copy is returned. All right. Lastly, the interface provides functions to inform the VM that the native code no longer needs to access the array elements, and these are the release functions. And again, when a JNI function returns a raw pointer, we have to use one of the release functions that is associated with the original function. When you call these functions, the system either unpins the array or it reconciles the original array with its non-movable copy and frees the copy. So we said that in the get double array elements, it also has a release double array elements and J array, C array, or basically the pointers. And what this does, when we get the elements, this is a copy, right? Gives us a pointer to a copy. But why do we need to release it? When we release it, two things happen. One, it copies back the original pointer copies back the array, the point, and then to the copy, because using this raw pointer, we can change the content of the copy. So when we use release double array elements, and then JVM takes back this pointer and copies the elements back into the original one, so that our changes are reflected in the original array, right? So another copy actually happens. So with this get double array elements, two copy, one behind the scenes by JVM because it gives us a pointer to a copy, and then when we release it, it first copies the elements back to the original array and then deletes this pointer, this array on the Java heap, which is very bad. Two copies happen, and if the array is very large, this becomes very inefficient. All right, so when you call these functions, the system either unpins the array, and unpins the array happens with the critical access. Get primitive array critical, it gives us a raw pointer. Release primitive array critical, basically it just basically it unpins. It just there is no copying happens. All JVM does in this case for primitive array critical, when we release it, it just tells garbage collector that we are done with this. It's not pinned anymore, so you have the freedom to move it in the Java heap if you want to. This release doesn't do anything in particular in terms of copying. It just tells the garbage collector that it can start moving things around if it needs to, right? So it unpins the array, or it reconciles the original array with its non-movable copy and frees the copy. Our approach provides flexibility. A garbage collector algorithm can make separate decisions about copying or pinning for each given array. For example, the garbage collector may copy small objects but pin the larger objects. Okay. A JNI implementation must ensure that native methods running in multiple threads can simultaneously access the same array. For example, the JNI may keep an internal counter for each pinned array so that one thread does not unpin an array that is also pinned by another thread. And again, this is more the advanced topic on multi-threading and how we deal with JNI when we do multi-threading. This is a topic that we don't normally use in our JNI applications. That's why I didn't really discuss them in my lectures. Note that the JNI does not need to lock primitive arrays for exclusive access by a native method. Simultaneously updating a Java array from different threads leads to non-deterministic results and all the race conditions and whatever. Accessing fields and methods. So let's go to fields. And we said that again, the mechanism is pretty much identical to the Java reflection. So the JNI allows native code to access the fields and to call the methods of Java objects. The JNI identifies methods and fields by their symbolic names and type signature. All right. So a field has a name, and first of all, if we want to access a field of an object, first we have to tell JNI or JVM to which object, which class we're talking about, which means we have to get the meta information of that class, which means we have to get meta information through a J class. And the way we get the J class or the meta information is to tell JVM to find it on the class path and pass in the fully qualified class name as a string, and the separator is forward slash. So the first step is always to get the meta information so that JVM understands which Java class we're talking about. And then we can say get field ID or get a static field ID, depending on we're talking about a static field or a non-static field. Static fields are class level fields, so they get a J class reference. Non-static fields are object fields, so they get a J object reference. And the fields can have the same name, but their type can be different, right? So there is no restriction on so fields can have the same name if their types are different. So just the name is not enough to uniquely identify a field. So both name and signature have to be specified, and they are specified as strings, string literals, for example, and the signature is a fully qualified name, right? So a string is L semicolon and in between Java /lang/string. The JNI identifies methods and fields by their symbolic names, whatever is in the source code, and type signature, which is the fully qualified name of the type. A two-step process factors out the cost of locating the field or method from its name and signature. For example, to call the method f in class CLS, so setting objects fields and then calling methods. Again, very similar to reflection, we get the J class and then get method ID, right? So for fields, we get the field ID. For methods, we get the method ID. That tells the JVM where this method pointer is inside the class. This is the offset from the object pointer, that is the header of the object. For example, to call method f in a class CLS, the native code first obtains a method ID. This method ID is just an offset, right? And we can use this to call this many times with a extremely low overhead, because once you know the offset, you tell the JVM, okay, go to this object, which it already knows, and go to this offset from the pointer, the header of this object, and that's the function pointer for this method. Get method ID, so environment or JVM get method ID, and then we pass the J class again, because that's the meta information, the name of the method and signature. And basically the reason that we need a signature for a method is that two methods can have the same name but different parameters, which is method overloading, and Java allows method overloading. That's why the name of the method is not enough to uniquely specify the method. We have to tell it this method and this signature. So J method ID, environment, get method ID, we give it the J class, the name of the method, and the signature. For example, is f takes an integer, and the signature of a method is its parameter signature in round brackets and then its return type, right? So if the parameter signature is void, it doesn't take any parameters, we don't write capital V. We just write basically nothing in round brackets. But the return type, if it's void, we have to specify it with capital V, right? So for return type void, we have to specify it. For void parameters, we don't specify, right? So the signature is, the method signature is round brackets, parameter signature, and then the return type. So we get the J method ID, which is the offset from the header of the object, the native, and this is not a static. So this method ID for a non-static method. If it's a static method, we say get a static method ID. The native code can then use the method ID repeatedly without the cost of method lookup. So J double result, call double. So once we get the method ID, for methods, in order to call them, we just use the call. Call, if it's a primitive type, we use the type call some type method, call double method, call integer method, and we pass the J object or J class depending on whether it's static or not. If it's a static, we have to say call a static some type method. If it's non-static, we don't have the static in the name of the function. Call double method, for example, J object, J method ID, and then we have an ellipsis or a var arg released, variable argument released, that correspond to the Java types, J string, J int, okay? So here this object, so call this double method on this object. This is the method ID, so the JVM knows which method, at basically where is the method pointer, which is basically this method ID, and then this is the first argument, which is a J int, and this is a string which is of type Java string or J string, right? Remember, the types must match the Java types, not C++ types. So what if the return type of the method is not primitive? So if it's a primitive type, so basically this type specifies the return type. So JNI provides two types of function calls for methods. One is calling a method, Java method, that returns a primitive type. So we say call double method, which means this we're calling a method that returns a primitive double. If the method returns some sort of Java object, then we have to say call object method. Call object method means we're calling a Java method that returns an object type, right? And then call object method returns a J object. Then we can typecast it to whatever, J string or some other type if we want to, right? So a field, what about field? So for fields, we get the J class, get field ID. For field, instead of call, we use get type field. Get double field, get integer field, and just the J object or J class and J field ID. There is no parameters because fields just field are specified by which object or class and what is the offset of that field inside the class binary. If it's a field that is a Java object, we say get object field, which means this is a field that is actually a Java object, right? So fields and method, the JNI functions are distinct by type, whether it's a primitive type or a object type. A field or method ID does not prevent the VM from unloading the class from which the ID has been derived. After the class is unloaded, the method or field ID becomes invalid. The native code therefore must make sure to keep a live reference to the underlying class or recompute the method or field ID. If it intends to use a method or field ID for an extended period of time. The JNI does not impose any restrictions on how field and method IDs are implemented internally, right? That is tied to how objects are internally laid out in the memory by the JVM. Reporting program errors. The JNI does not check for programming errors such as passing in null pointers or illegal argument types. Illegal argument types includes such things as using a normal Java object instead of Java class object. The JNI does not check for these programming errors for the following reasons. Forcing JNI functions to check for all possible error conditions degrades the performance of normal or correct native methods. Remember, we're going to native for performance, so JNI relaxes a lot of things. In many cases, there is not enough runtime type information to perform such checking. And we saw that in terms of the when we compared the Java reflection versus the JNI accessing to fields and methods, we saw that obviously in Java API, the reflection API inside the Java, it does a lot of checking to make sure that we can't access, for example, a private method or whatever. In JNI, there is no such thing. We can directly access any private type or private method with no problem. Most C library functions do not guard against programming errors. The printf function, for example, usually causes a runtime error rather than returning an error code when it receives an invalid address. Forcing C library functions to check for all possible error conditions would likely result in such checks to be duplicated once in the user code and then again in the library. The programmer must not pass illegal pointers or arguments of the wrong type to the JNI functions. Doing so could result in arbitrary consequences, including a corrupted system state or VM crash. And we've seen in my lectures many times I intentionally crashed the VM to see what happens. So VM creates a log, dumps a crash log on your disk so you can examine what went wrong. Was it in the Java stack or native stack? What was wrong? Java exceptions. We've seen that there's not much to Java exceptions in JNI. It's very easy. JNI provides 4 main functions to deal with exceptions. The JNI allows native methods to raise arbitrary Java exceptions. So we can handle exceptions that occur in Java. We can also throw new exceptions directly in C++. The native code may also handle outstanding Java exceptions. The Java exceptions left unhandled are propagated back to the VM. And we saw that in my case, when we saw that if we don't handle the exception, when JVM comes back to Java, it freaks out, right? It freaks out and then it starts doing a stack unwinding. Immediately goes out of the calling method and then it starts doing a stack unwinding. So it's better to handle the exception inside the C++. Exception and error codes. Certain JNI functions use the Java exception mechanism to report error conditions. In most cases, JNI functions report error conditions by returning an error code and throwing a Java exception. The error code is usually a special return value such as null that is outside of the range of normal return values. Know that null is just a macro in C, right? And it maps to 0 integer or 0 long. Therefore, the programmer can quickly check the return value of the last JNI call to determine if an error has occurred, or call a function exception occurred, which gives us a JThrowable handle, which is a pointer. It could be null or not. If it's null, it means basically the exception object is null, which means no exception was occurred. Call a function exception occurred to obtain the exception object that contains a more detailed description of the error condition. There are 2 cases where the programmer needs to check for exceptions without being able to first check an error code. The JNI functions that invoke a Java method return the result of the Java method. The programmer must call exception occurred to check for possible exceptions. But this is not necessary. We can use exception check, which returns a JBoolean instead of JThrowable pointer, right? So if an exception occurred, or basically if an exception is currently at the top of the Java stack, we can check for it, right? If you want to get really a handle to that Java object, Java exception object, we can use exception occurred to get a JThrowable. But for just checking the exception, we use exception check. Some of the JNI array access functions do not return an error code, but may throw an array index out of bound exception or array store exception. In all other cases, a non-error return value guarantees that no exception has been thrown. Asynchronous exceptions in case of multiple threads, and again, this is a topic that we didn't discuss, which relates to multi-threading. In cases of multiple threads, threads other than the current thread may pose an asynchronous exception. An asynchronous exception does not immediately affect the execution of the native code in the current thread until the native code calls one of the JNI functions that could raise synchronous exception, or the native code uses exception occurred to explicitly check for synchronous and asynchronous exceptions. So this exception occurred checks if basically gives you a handle to a JThrowable object, or basically a Java exception object that might have been thrown by the current thread or other threads. So it checks for both of them, synchronous and asynchronous exceptions. Note that only those JNI functions that could potentially raise synchronous exceptions check for asynchronous exceptions. Native methods should insert exception occurred checks in necessary places, such as in a tight loop without other exception checks, to ensure that the current thread responds to asynchronous exceptions in a reasonable amount of time. Exception handling, and again, these 4 functions, keep them in mind. There are 2 ways to handle an exception in native code. The native method can choose to return immediately if we don't clear the exception, then or basically if we just in the native code we write return with some, if we return with some value, we immediately return. The native method can choose to return immediately, causing the exception to be thrown in the Java code that initiated the native method call. The native code can clear the exception by calling exception clear, and then execute its own exception handling code. So if we check that an exception occurred, and if so, we just immediately return from a native call with some value, maybe garbage value, then the exception will be thrown in the Java also. So we can use a try catch in the Java and handle the exception in Java, or we can use exception clear and then write a code in C++ to handle a Java exception. After an exception has been raised, the native code must first clear the exception before making other JNI calls. And this is very important. I mean, obviously we can, before clearing the exception, we can call the exception describe. So we can print it on the console. And then we have to first clear it before doing any other JNI call. When there is a pending exception, basically when until or before we call the exception clear, there are some JNI functions that are safe to call. The JNI functions that are safe to call are the following. And these are the ones that, first of all, these four that deal directly with the checking and handling exception occur, describe, clear, check. These four directly handle the exceptions. Or other functions that deal with releasing some resources, release a string chars, release a string UTF chars, release a string critical, release type array elements, release primitive array critical. All these release functions, so releasing memory resources, these are safe to call even if an exception occurred and we haven't cleared it yet. Delete local ref, delete global ref, delete weak global ref related to garbage collection and stuff. And again, all these are related to object references and garbage collection. Monitor exit, push local frame, pop local frame. I think these are more related to multi-threading, right? But again, there are three types. When an exception is pending, there are three types of functions that are safe to call. One, the ones that handle the exceptions, the ones that release memory resources, and the ones that talk to garbage collection, right? So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.